Let's come back to the main topic, but this time for discrete time systems, and in particular discrete time linear systems in the form of xk plus 1 equal to axk. The analysis is very similar. We still want an energy-like function, and we know a good candidate is this quadratic form. It has a good potential to be an energy-like function, the Lyapunov candidate. Now, this function is defined with k as the time index, so it's not continuous, it is discrete. And then when we evaluate the increase of energy, or the trains of the energy function, we look at how it changes with changing index, with changing time index, or in other words, we look at the difference between x transpose k plus 1 p xk plus 1, and then this. So far, this is just our design of the Lyapunov candidate. We haven't used any properties of the system yet. And we don't have a Lyapunov equation yet. The key about Lyapunov analysis is you bring in the system dynamics into the Lyapunov candidate that you proposed, and then look at how things will simplify. If you plug in the system dynamics into here, you're going to have x, so p, xk plus 1 becomes axk, and then on this side is x transpose k, a transpose. The second term doesn't change, but once you substitute the system dynamics in here, immediately you can conclude that this difference, this change of the energy-like function is actually quadratic. It can be written in this form. You can combine the matrices in the middle, and then on the left and on the right, you're left with x transpose k and xk. So it's quadratic. You have the change of the energy to be in a quadratic form. So what do we want? We want, let's define, if we define this as q, as negative of q, then we want q to be positive definite. If q is positive definite, then that means the change of the energy is negative definite. That means the energy will keep reducing. This equation is the discrete time Lyapunov equation. It's different from the continuous time version. You can see A appears in a lumped form on the left of the first term. And then it's negative p here, and then negative q on the right-hand side. So it's different. The solution will also be different. The procedure is select Q to be identity matrix, solve for P, and then if P is positive definite, then you can conclude asymptotic stability. So that's the recipe over here. In more details, if you plug in Q equal to identity and try to solve this, you will realize that you see P, this equation is also linear with respect to P. If you look at P, there's no P square or sine of P or any other nonlinear terms about P. So this equation is linear with respect to P, meaning that it's very easy to solve for our case. This equation is not linear with respect to A. You can see A appears in this form. In this first term, you have to multiply elements of A. You will have quadratic elements in about A. So that's different from the continuous time case. Continuous time, the Lyapunov equation is linear with respect to A, but discrete time case is not. Okay, now we have talked about how the energy will change along the state trajectory. The way, more formal way to say this is the change of V, the Lyapunov candidate, along the trajectory of the state of the system dynamics. It's along the trajectory because we substitute A xk plus 1 equal to A xk, the system dynamics, into here. If we don't do this step, this is just the mathematical difference, the mathematical change of the energy-like function. Once you do this, it becomes the change along the system dynamics, and that makes the whole difference. And then we have the theorem over here. For the discrete time system, the origin is asymptotically stable if and only if exists a positive definite Q such that the Lyapunov equation has a positive definite solution P.